Here's the first of some promised video snippets. I'm going to probably try to send you 3 of them. I'll cover the first 4 problems and this one, and then 2 more snippets. Try to make them not so long. I want to tell you that you could call me at 440-666-1953. I made a joke about another number. Email would be the best thing if you just sent me email with any kinds of questions, or I'm in the office all the time. But here we go. This was essentially the notes that I used yesterday for our review session. And I'm going to send you these notes. I'm going to email these scanned. And I'm going to probably do it after I write on them a little bit. In problem 1, we had our typical, the velocity of the plane relative to the ground is the velocity of the plane relative to the wind, plus the velocity of the wind. And we knew the plane was going east. We knew that the wind was going west of south. We could make our triangle. And one of the main points I wanted to make was that when you're using the law of sines, you'll actually get, of course, a value for the sine of the angle. And in general, there are 2 different quadrants for that. Well, your triangle, you'll go back to your triangle and you'll easily see which quadrant it is. In this case, it's the small angle rather than the large one. But keep that in mind when you're using the law of sines, for example. Oh, let me say, once and for all, draw a picture. In this case, the problem itself cries out for a picture, so we do that. But in some of the cases, you'll just do so much better if you'll sketch out what the thing looks like, as you'll see later when I talk about some of the later problems. In problem 2, it was just like the monkey ball problem. We match up the x and y coordinates of the car and the truck, and the car goes in a straight line, the truck, at constant velocity, the truck accelerates, and the question is, do they meet? Or would one have gone past this point before the other got there? The amusing thing that I mentioned in the review was that if you look at the formula and you call D capital R, you call A G, you get the same answer that we had for just a good old level ground trajectory thing as to how far did we go given an initial speed, given an initial angle. And that's because if I just move this acceleration by subtracting it from the truck so it's at rest, then the car just looks like a trajectory problem. All of this is similar to planes dropping packages so that they land exactly on a moving truck below here. And this is a typical trajectory intersecting problem. In problem 3, it gets more interesting. Again, if we draw our picture, we have an instantaneous collision where the smaller body bounces back. It bounces back. This is a one-dimension, head-on guy. And that happens instantaneously before the big body starts to move, so we can forget the springs. The second part is now that big body has gotten some momentum and therefore some kinetic energy, and that kinetic energy can get converted completely into potential energy and compressing the spring as far as it goes. In doing the calculations, you can just go and trot out the formulas that we've derived once and for all. I went ahead and used a relative velocity before is minus the relative velocity after thing that we derived only for one dimension and only for elastic scattering. It just was kind of an easy thing that I could derive, and so I re-derived what you would get from the formulas. I did have a comment about the second stage. It's just the kinetic energy change is completely equal then to the negative of the potential energy change. I lose kinetic energy, it's negative. Therefore, with that minus sign, delta U is positive. Sure enough, I compress the spring. And by the way, you know from the original work-energy relationship we had, delta K equals any net work on the thing. Well, in this case, it's the work of the spring on 4M, but it's negative. Sure enough, we do work on the spring. Our big body does work on the spring. And sure enough, this work of spring on 4M is minus work of 4M on spring. And just keep that in mind then, that what came in here in the delta K was work on our body, but we can also talk about the work of the body on whatever external system was producing the force on us. The frequency formula, just remember, is your effective K over your total mass, and it's not just K over M. It depends upon what the spring constant is. Finally, in problem 4, this was my chance to tell you two things. When you have a collision, you gotta be told, is it elastic or is it not? We gotta have some information about that. In this case, we are told so much about what happened after the collision that we can just go ahead and use momentum conservation. We don't have to think about kinetic energy conservation, and we can check to see if kinetic energy is conserved afterwards. The one thing you do know is for all these collisions, this one and this one, momentum's conserved. That's golden. And speaking of golden, although these triangles are trivial, throughout these practice problems, we've got golden triangle calculations all over. When you've got some vector, momentum, velocity, or whatever, and you're looking for the components of force, you choose the legs of a right triangle in the directions you're interested. In this case here, it'd be horizontal and vertical. And you know this plus this equals that. So you'll know exactly the sign on these components. You use your cosine sine calculations to get the components after identifying some angle in this triangle from your original situation. In this case, these are trivial triangles. Notice that in this problem, although I did it with components in the solution you got, the initial momentum is the final of B plus the final of A. And that's a triangle that proves the planarity. And your triangle is a right triangle, and that gives you a quick calculation like our problem 1 of all sorts of all the results. And if you look at them, sure enough, they look Pythagorean. But again, this you had to check. It wasn't elastic when you looked at the kinetic energy, sure enough. And so you won't necessarily have, you know, these angles relationships that we had, remember, in the first problem of exam 3. All of that discussion was only for elastic cases. Remember, when the masses are equal and one guy's at rest, then we had that 90 degrees. When, you know, the masses are unequal and elastic, then we could say something about their opening angles. But just remember that that was only elastic and one of the particles at rest for all of that discussion. Here too, it was at rest. But this opening angle could be anything when we're not sure, just subject to momentum conservation, but when we don't have elastic. Okay, I'll come back with another snippet later.